My name is Shubham Sharma and I am doing PhD under the supervision of Dr. Haleen Daya from Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar, India. The topic of my today's presentation is high twist proton distributions in the light front Quark-Diquark model. So here is the outline of my talk. First I will start with the brief introduction. Then after that I will describe about the model which I am using, which is light front Quark-Diquark model. And after that I will discuss about the TMD correlator function and its parameterization equations at higher twist, and at the end we will do some discussion. So the QCD, basic idea of QCD is to describe hadrons in terms of quarks and gluon degrees of freedom. So we are going to work with small particles and at higher energies. So this means at that time special theory of relativity came into picture, which says that space and time are not invariant quantities. Rather, space-time collectively is an invariant object. And here we have three different reasons depending upon the velocity of our particles. And yes, so it is clear that we are going to work with light cones. Now the question is which form we should use. There are three different forms: instant form, front form, and point form. And with their different initial surfaces, we are going to work with front form. Why so? Because it is an ideal framework to describe theoretically the hadronic structure in terms of quarks and gluon degrees of freedom. It has a simple vacuum structure. That is, the vacuum expectation value is 0. That is, no particle antiparticle can pop up by itself. Second, we knew that a dynamical system is characterized by 10 fundamental quantities, which are energy, momentum, angular momentum, and boost. In this case, 7 out of them are kinematical. It is good to point out here that in other cases, the number of kinematical variables are 6. The third one, it has a simple dispersion relation. It does not contain any square root factor. So we are going to work with the light front. And what are the light front coordinates? In Minkowski space, we have 4 variables, 1 time variable and 3 space variables. When we combine this longitudinal space variable with time variable, we get light front time and light front longitudinal space variable. And the remaining 2 variables combine to form a transverse variable. Similarly, we can define the longitudinal momentum and light front energy. So the maximum amount of information which can be obtained theoretically about the hadronic structure from any is encoded in generalized Parton correlation function. GPCFs are dependent on 4 momentum of hadron and 4 momentum of quark. When we integrate the generalized Parton correlation function over the light cone component of the Parton's momentum, we get GTMDs. GTMDs are function of x, p-pup, and del. X is the longitudinal momentum fraction carried by the parton, p-pup is the transverse momentum of parton, and del is the momentum transferred during the process. And from this GTMDs, we can obtain all the distribution functions given here following the legend. As an example, we can obtain the TMD by applying the limit del equal to 0. That is the forward limit. We get the TMDs. And other distribution functions are transverse momentum spin densities, PDFs, charge, form factors, GPDs, and transverse momentum form factors. So coming to the model I am using is light front Quark-Diquark model. So this model assumes that the proton is made up of 3 constant quarks, and whenever the scattering happens, it happens with 1 quark and remaining 2 quark will act as a spectator. So it has it is made up of isoscalar scalar diquark singlet, isoscalar vector diquark, and isovector vector diquark, where S and A are used to denote scalar and vector diquarks. Their isospin has been denoted on the superscript, and this model has been built by Tanmay sir and Dipankar sir. So the Fock state expansion for the case of scalar diquark is written like this, where nu is U and D for up quark and down quark, where this represents the state of 2 particles having quark helicity lambda q, spectator helicity lambda s. These are the momentum coordinates of quark. And the wave functions which are used in Fock state expansion are written like this, where ns is the normalization constants, and we will discuss about these files later. Similarly, we have Fock state expansion for the case of vector diquark, and similarly in this case lambda q is the quark helicity, lambda d is the diquark helicity, and lambda diquark helicity has a triplet state. These wave functions are written like this, where n0 and n1 are the normalization constants. Again, we are having the same files. Same for jz is equal to -12, we can rewrite the wave functions. So these light front wave functions have been adopted from light front ADS QCD, and and it is some kind of modification by the parameters A, B, and delta. So what are these parameters A, B, and delta? These parameters have been fitted by using Dirac and Pauli form factors data, and the values of normalization constants are given in this table. So we can see that for a down quark, we do not have contribution from the scalar type quark. And the ADS QCD scale parameter kappa is chosen to be 0.4. These are the value of normalization constants. So at this point, it is good to point that whatever calculation I am doing is corresponding to the Venzura-Wilczek terms or the mass terms. We are planning to include the pure tilde terms or pure twist 3 contributions. So right now we don't have done this, but we will do that in future. So the TMD correlator, unintegrated TMD correlator for light front formalism is written like this, where this is the final state hadron, this is the initial state hadron, these are the quark field operators, and the momentum of proton, step quark and diquark can be written like this. This equation has been taken from Meshner-Metz Jehab paper. So these are the parameterization equations for proton at twist 3. The blue ones are the T even TMDs and the red ones are T or TMDs. Here we have different Dirac matrix structures on the superscript. Similarly, we have TMD parameterization equations at twist 4. Similarly, in this case, we have T1 TMDs are in the blue color and T or TMDs are in red color. So when we solve these parameterization equations, we get a table like this. In the first column, we have different Dirac matrix structures, and the different columns corresponds to the different combination of helicities taken in hadron helicities taken in quark-quark SIDS correlator. So the blue ones are the unpolarized, blue ones are the T1 TMDs, and we have solved those TMDs equations. So coming to the result discussion, when we have solved this parameterization equations and the correlator, we get the explicit expressions of TMDs. These are the equations for XE, F-perp, GL-perp, GT prime, GT-perp, and HL, ST, and ST-perp for all T1 TMDs. Similarly, we have solved for T1 TMDs at twist 4, which is F3, GL, HL perp, GT, S3T, and S3T perp. So these are the TMD relations which we have found, and they have also given in, these are called as equation of motion relations at twist 4. At twist 3, on the left hand side we have twist 3 TMDs, and on the right hand side we have twist 2 TMDs. These tilde terms correspond to the pure twist 3 contributions, and these are 0 in this case because we are because in our model there are no quark model interactions. So tilde terms corresponds to 0, and all the results are just Venzura-Wilczek approximation. Similarly, we have found some relations at twist 4. Here the twist 4 TMD F3 is related to F1 TMD. F3 TMD is the unpolarized TMD. We will discuss about this later. So the average transverse momentum. We have calculated the average transverse momentum, an average scale transfer, an average scale transverse momentum in our model, and compared them with the available data. Like we have compared P-perp for light front Quark-Diquark model and compared them with the consistent quark model. This consistent quark model result by Serdi-Clores and others. So as suggested in light front consistent quark model, that for U and for E and F-perp, they have the same values, and similar results have been shown in this, although the average transverse momentum is slightly different, which is obvious because the model is different, and all the values are exactly or more or less same, but few fluctuations are there. Yeah. Similarly, we have calculated the average scale transverse momentum, and here we have bag model results for P-perp average. The bag model does not use the same formula for this. They have a slightly different formula because at high P-perp, their results diverge, so they use some kind of approximation to average transverse momentum, and they have collected it. They have calculated it in different ways. So here we have different values, and we have compared with light front consistent quark model and bag model results. So very less data has been available for twist 4 TMDs, But yeah, in light front consistent quark model, they have done some calculations. So we have compared our result with light front consistent quark model, and we have found that the for p-perp case, the results are very similar. Also for p-perp square, it is different from what they are getting from light front consistent quark model. This has been taken from Cedric-Loris paper. So here we have compared all the different TMDs, unpolarized TMDs, which we are getting in the same TMD PDFs, which we are getting in our model. As you can see that for F1 has the maximum amplitude for both U and D quarks, and because F per TMD is related directly with this, so it has also the higher amplitude. But for the case of E unpolarized TMD E, it is diminished by the factor mass ratio. That's why their peak is very, very small. And in the case of twist 4 TMD, it has a square of mass ratio. It is just approximately to square of mass ratio. That's why it is very, very diminishing factor. So we have compared our results for flavor combination E with the class data and light front consistent quark model data. Our model scale is very, very low. It is at 0.09 giga electron volt. So it is not justified to compare it with this. But even then, we can see that at higher value of longitudinal momentum fraction, there is some kind of overlapping with the data, and these are the this flavor combination extraction has been done by Courtois from beam spin Asmita's data, and all these other values are at 1 GeV square. So we have talked to many people regarding the evolution of this E, but we came to know that we cannot use the leading twist evolution equations for this TMD. But even then, to give an idea, we have also talked to other people. They are saying that we can use the lower twist evolution equations if our TMD has a kind of similar behavior to the lower twist. So to give an idea, we have compared it at 1 GeV square. So here we can see at 1 GeV square, there is a kind of overlapping with the data. But yeah, underlining that, we should check by considering the higher twist evolution equations, and we are working on that. Okay. So here is the comparison of our results with the bag model. It should be good to point out here that the bag model calculations have an amplitude very, very higher than our results. But concerning the same thing, we do not have any evolution till now. So HL-TMD PDF is finite comparing to our results. So we have compared our results with this TMD PDF. And here red corresponds to the total contribution from both the dynamic terms and the Venzura-Wilczek, and blue corresponding to the Venzura-Wilczek term of HL-TMD. So here we can see that for the bag model result, the peak or the shift is at the higher value of longitudinal momentum fraction x. So more data, when more data will come, we will see that how we can proceed regarding the interpretation of this. So we have at the end given some few plots of TMD PDFs. Here we have GL perp, GT prime, GT perp, and ST. The longitudinal polarized TMDs shows the kind of quark flavor symmetry, whereas the transversely polarized TMDs show anti-symmetric behavior. At most of the cases, we have more contribution from U quark, more magnitude from U quark rather than the D quark. But in few cases, we have large contribution from D quark because in that case we have different terms which are cancelling each other. Also at the low x, we are seeing some kind of this behavior, which is due to the 1 by x kind of thing, or when we integrate it to some kind of this thing. It is we should see whether these kind of things are in at fixed p-per value of TMDs or not, so that we can say that. And yeah, at the end, I want to thank the organizers for this wonderful school and workshop. we have a very good time here, very nice food, and we value all the discussions, all the feedbacks which we have here. And yeah, thank you.
Hello. So is there any correlation between this leading order distribution function and this higher twist distribution functions? I mean, can one go from higher twist to lower twist in some particular limiting cases?
These are the TMD relations. These are the TMD relation connecting the higher twist TMDs with the lower twist. And also, yeah, these are the equation of motion relations. We are also working on some other relations, but we cannot reveal it at that time. So you will see it in some time.
Okay. And is there any interrelation between those TMDs? I mean,
yeah, there is
some
yes.
Okay.
Yes.